the black holes will be the hottest things around. And when they're the hottest things around, pretty cold, but hottest things around, they will radiate away. And as they lose energy in radiation, E equals mc squared, they lose mass in radiation. Therefore, they get smaller and smaller and smaller and smaller until finally they disappear with a pop.
It's a point in space where all the mass is located in an infinitely small volume, meaning you get something with an infinite density. It's almost a mathematical impossibility.
Yet, we think that general relativity is probably not right, probably not the final answer, probably not the complete theory of gravity. And the singularities at the centers of black holes are a major reason why.
But if you travel faster than the speed of light in the direction that you're falling in this new abstract coordinate system, you don't hit the singularity, you pass through a sort of mirror event horizon and you end up in a mirror universe.
So black holes seem to be able to be a switch that can modulate the formation of stars in a galaxy. So that's pretty fundamental. So this is new understanding.
What is a black hole? Well, a black hole is, in some sense, a mathematical construct. So black holes really took off beginning of the 20th century when Einstein wrote down the equations for general relativity. And from that point, there was, almost an arms race to just solving that equation. So Einstein providing with the framework, and then all sorts of different physicists tried to solve the equation to find all sorts of things about, the universe. And one of those solutions that you find to the equation is something that is a black hole. So a mathematical singularity, meaning a single point where the curvature of space-time caused by general relativity becomes infinite. In other words, it's a point in space where all the mass is located in an infinitely small volume, meaning you get something with an infinite density. It's almost a mathematical impossibility, something you can describe with an equation. But if you think about it in terms of physical terms, it makes no sense. How can something have infinite density? Yet this is what a black hole is based on these equations. So for a long time, the black holes were seen just as a quirky mathematical construct.
So what is a black hole? Beyond the mathematical solution, now that we have these physical entities, how do we think about them? So, sort of broadly, the three ways one can think of them. So in the 1930s, Chandrasekhar showed that the end state of very massive stars, so a star that is born with a birth mass of 10 times more massive than our sun, will exhaust all its fuel, have an explosion, end its life, and leave a black hole as a corpse. So that's one way. So very concentrated, dense, gravitating material would be the result of a massive star's death. That would be a black hole. So that's one way to think about a black hole. But I think it's best to think about the black hole as a place. Although as astronomers, we like to think of it as a thing because we are measuring it. As you'll see, these are views that can actually be reconciled quite easily. Complicated, but can be reconciled. So another way to think about black holes is to think of the analogy with the intense gravity. I keep telling you that gravity is very intense because the matter is so condensed that gravity is very intense. So we look at the Earth and we are launching all these satellites, right? And why do we boost them? We boost them so that they can have a velocity, a speed that is 11.2 kilometers per second. That's the escape velocity for a rocket to free itself from the grip of Earth's gravity, right? And so if you now just imagine and extrapolate in your head that if you had something, so that's the Earth, the mass of the Earth, and that's the escape velocity. If you think of an object that if you condense all the matter in the Earth, the entire Earth, all of us, into the size of a penny, that would give you the kind of attractive force of gravity, the strength of gravity. From that, the escape velocity would be the speed of light. So that's the basis when people say not even light can escape a black hole. So that's what we mean. The escape velocity from a black hole, from the event horizon of a black hole, is actually the speed of light. Then the final way we want to think about it, and this is what Einstein really thought us, so I was sort of building up, move from more real things to the mathematical description. So one way to think about it, think of black holes is as sort of punctures, literally sort of punctures not literal punctures, but sort of analogy is punctures in space-time, very deep distortions in space-time. And this is what Einstein was able to do with general relativity. As I said, connecting the shape of space to matter and motion. So if there was no matter in the universe, our entire universe can be described by a flat sheet. Okay? And when I say flat sheet, it's a sheet not just of space, but space and time sort of commingled together. And now when we do have matter, so for example, you have the sun, it sort of creates a divot in that sheet. Right? So you see that little pothole that's generated whenever you have matter. Now, if you have a neutron star, in contrast to the sun, which is much more compact, much more dense, right? So notice it makes a deeper divot in the fabric of space-time. You think of a black hole as really making a puncture, a very sharp divot in space-time. So these are the sort of three different ways of thinking about black holes, both mathematical and real.
Now, Milky Way galaxy, there is an absolutely huge black hole, which has a mass. Black holes have masses. This mass is about 4 million times the mass of the sun. So it's pretty enormous. And it sucks other things in. Gas and stars now and again will fall into it. And once they fall in, they can't escape. And that's one of the implications of Einstein's general relativity. So we come to believe in this. It took, I may say, cosmologists quite a long time to take them seriously. But they did eventually. And now they're seeing them all over the place. The Andromeda Galaxy has a black hole, which is a good deal, I forget whether it's 40 times, something like that, as big as ours. Those objects, the black holes, are where most of the entropy is. So we have entropy finding its way into these black holes. Okay, now the universe expands, some things fall into black holes. Sometimes the black holes, things will escape from the black holes, but on the whole, the black holes will dominate what used to be the galaxies. And then what will happen? Well, as the universe cools down, the black holes start to radiate away. You see, there's a thing called Hawking radiation. Stephen Hawking showed that black holes, well, he calls them black holes are hot. I think it's a bit of an exaggeration because they're not that hot. In fact, is it worth thinking about how hot they are? The hottest ones are the smallest ones. And the smallest ones we have any good astrophysical reason to believe in are maybe about 10 times the mass of the sun. Those are the hottest ones. How hot are they? Well, if you think of the coldest temperature that's ever been artificially made on the Earth, and that's pretty cold, you're in the right ballpark. It's around about that. So not very hot. The big ones are much, much colder. The supermassive one in our galactic center would be enormously colder than that. Essentially absolute zero. But as the universe expands and expands and expands with its exponential expansion, it will cool down. The microwave background cools down, and then the black holes will be the hottest things around. And when they're the hottest things around, pretty cold, but hottest things around, they will radiate away. And as they lose energy in radiation, E equals mc squared, they lose mass in radiation. Therefore, they get smaller and smaller and smaller and smaller until finally they disappear with a pop. Now, I'm using the term pop rather than bang because on cosmological scale, it's nothing. Okay, it wouldn't be nice for it to go off in this room like that, but nevertheless, it would be pretty small on astrophysical terms. So that's what happens to these black holes. How long will it take for them all to disappear? Well, you've got to think about the biggest ones, which will be the coldest ones, and therefore they will the last ones to begin to get cold, and how it take the longest to get cold to disappear. I mean, the biggest ones will take a long time. They will take around about, to get the rough idea, 10 to the 100 years. So it's a sort of googol years. If you know what a googol is, write 1 0 0 0 0 with all 100 zeros. And that will be roughly within, I don't know how many orders of magnitude, but you can get a rough figure. For that kind of figure, you have to wait that long before these black holes go off pop.
So black holes are essentially a very special place where the intensity of gravity is so high that not even light can escape. And to give you a sense of notion, right, so it's called this notion of escape velocity. So you must have all been watching the SpaceX, Blue Origins, all these guys launching rockets and NASA launching rockets, right? So why do we need rocket fuel? We need rocket fuel for these rockets to escape the grip of Earth's gravity. And to do that, we need to accelerate them and speed them up at launch with a speed of 11.2 kilometers per second. That is Earth's gravity, right, to escape. Now, the escape, if you imagine now that you have an object whose escape velocity is not 11.2, but the speed of light. That's what a black hole is, okay? But what has remained stable conceptually is that if a star has a large birth mass, then it would go through a red supergiant phase, it would go supernova, and it could leave one of two. Stellar death will have one of two options. It would either end up as a neutron star, so these are both very compact objects. That's quite different in terms of has a lot of magnetic fields, has a crust, or you end up as a black hole. So this is what we believe to be the structure. So this is what a very compact bit of matter does to the shape of space around it. And that's what a black hole is doing. And here are some fundamental properties. They're crazy, but they're beautiful, okay? And so this is that puncture. This is a schematic that shows you that you have this deep puncture. It's so dense, it punctures space-time. But it has this kind of boundary, this boundary that you see in dashed, which is called the event horizon. So that's like the border, if you will. It's a periphery. Once light or matter or anything passes that boundary, gets close and passes that, is the point of no return. Okay? Then there is a region around it, which is the light horizon, where light would be in eternal limbo and it would keep going around. And that's outside the horizon. And then there are, of course, regions where the gravity of the black hole is no longer dominant when you're far enough away. Light just grazes past. So you can see immediately that perhaps the presence of black holes could be detected from the effects that they inflict on light that passes by.
So we have this fundamental question, right? So if we observe black holes out there in space, we observe lots of them that are, with stellar mass, so about 1 times the mass of the sun. And then we have a lot of these black holes at the centers of galaxies. We believe at the very center of most galaxies, there is a supermassive black hole with, at least 1 million times the mass of the sun. The fundamental problem here with our astrophysics is that as of yet, we have not observed any intermediate mass black holes. It's like black holes come in extra small and extra, extra large with no sizes in between. And that really is a challenge for any mechanism that try to explain how we can form these supermassive black holes, whether it be by feeding small ones and make them go big, or by taking small one, making them merge to form bigger and bigger black holes. So I'm just mentioning this to show you just how, there are still some very fundamental questions about black holes, like how do we even make them, that we're still working on very actively in astrophysics these days. And the problem gets even worse about formation of these supermassive black hole when we look back out in space. So because light travels at a finite speed, there's this fundamental property of space in a tool us astronomers use all the time, which is that the further out in space you look, the further back in time you look as well. So if we look at distant galaxies, nearby galaxies first, we can look at the supermassive black hole at the center of the galaxies, and I'll tell you more about this image specifically in a few minutes. So we know that these supermassive black holes are at the center of most nearby galaxies. We see things like this, for example. We see galaxies, and then the thing at the middle here is the galaxy, and then this reddish, pinkish stuff is images of the gas that is being ejected out of the galaxy by the energetic black hole at the center. That's the stuff that the messy toddler, chucks back out, the stuff that doesn't go into the mouth of the black hole. So we see evidence for these black holes to be, at the center of most galaxies nearby. We see them if we look back in time up until about, only 1 billion years after the Big Bang. We still see them. In this case, these supermassive black holes are actively feeding which, there's a lot of gas that gets heated up in the region around the black hole. So they glow so bright that they outshine the entire galaxy they live in. So we can see them quite clearly, even that far back in time. And if we look as far as we can with the telescopes we have right now, up to only a few 100 million years after the Big Bang, we still see them. Right? Okay, it's maybe not super impressive, but this is something we're watching as it was just a few 100 million years after the Big Bang, one of the first ever galaxies to form, yet it already has a supermassive black hole at its center. So that really only emphasizes the problem of explaining how do we form these things, because there's really isn't that much time between the Big Bang and then these first galaxies that already have these supermassive black holes at their centers. So again, a very active area of research in astrophysics and something we're really thinking about quite a lot these days.
The existence of these singularities inside black holes, because I think, David, it goes to the question you're asking, it reflects one of the various ways in which modern physics is in a very strange situation. We have this wonderful theory, general relativity, that literally fits every piece of data that we have. There is no observation, no experiment that isn't, as far as we know, compatible with the predictions of Einstein's general theory of relativity. Yet, we think that general relativity is probably not right, probably not the final answer, probably not the complete theory of gravity. And the singularities at the centers of black holes are a major reason why. The similar singularity happens at the very beginning of the universe in the Big Bang. These are examples where the theory itself seems to be telling us that the theory is wrong. The theory
is because of the infinity, sure.
Yeah, because it describes physical quantities like the curvature of space-time, the density of matter, etc., which you would expect to be well-behaved and measurable, yet become infinitely big. And that's not only sort of worrisome all by itself, but probably not compatible with an ultimate quantum mechanical description of what's going on. So that's another reason why black holes are so important, not only to the physical evolution of the universe, but to the brains of theoretical physicists who want to try to understand better what's going on. Black holes are this wonderful, wonderful puzzle and paradox. And then the entropy stuff and the radiation stuff just builds on top of that in an interesting way.
So this is a black hole that has a massive black hole where it's actually triggering star formation. It's helping a burst of stars form. And then the other black holes I showed you, they actually prevent stars from forming. So black holes seem to be able to be a switch that can modulate the formation of stars in a galaxy. So that's pretty fundamental. So this is new understanding. So when I was doing my thesis in Cambridge, we didn't know this. Okay? So last 10 years, we've kind of figured out. We were still puzzling over what do they do? What do these correlations mean, right? So we've now seen that they have they may be very critical to the assembly of a galaxy itself. It turns out that the formation of a galaxy, when the stars form, how many stars form, may be regulated by a black hole. So the question is, how do black holes feed? So this is a slice from one of my simulations. This is so you have the disk that is going around the black hole. This is a front view. I've cut a slice through this. So this is the disk. The black hole is here, and matter seems to be feeding on to the black hole. So that's, as I said, accretion of gas. Another way a black hole might grow, this is my former PhD student's simulation, 2 spiral galaxies that each have black holes in their center that are growing. So you see the flickering in the center is their black hole is growing. So that shows you that it's feeding on gas. Then they keep collapsing into each other. So there's sort of this intricate dance of collisions. And you'll see that eventually the 2 black holes will merge. And just as I mentioned, when stellar mass, lower mass black holes merge, we saw the tremors in space-time that have been detected. The tremors in space-time that will come from the merger of these supermassive black holes is not yet detected. Because we need that detection apparatus that you had for LIGO on the ground, you need that in space. So that's coming. The European Space Agency and NASA have a mission called LISA, which is going to be able to detect, because it's very low frequency. It's so low frequency that we cannot detect it from Earth.
So I mentioned this term singularity as an infinite, like an age or boundary of space-time. And in a simple Big Bang picture, there's one sitting right at the beginning of our universe. But another place you find them is inside black holes. So if you follow the theory, then say a star collapses to form a black hole. It disappears into the black hole. You can't see anything. You can't see into the black hole. That's why it's black. Where does the star go? And imagine it's a perfectly spherical object, and it's got to go on shrinking, and it does shrink very rapidly, like in a few millionths of a second, it's gone. Where does it go? Then there's only one place it can go, down to a single point of infinite density. That's a singularity. You might say, oh, but it wouldn't be exactly spherical. But Roger Penrose and Stephen Hawking proved many years ago that it doesn't matter if you have departures, there's a singularity in there somewhere. Now, Lee Smolin proposed that maybe when stars collapse to form black holes, they don't just disappear from the universe altogether, that is, leave space-time or come to a boundary of space-time, that maybe those singularities are really like little wormholes that would connect our universe to another universe. So that's an old idea, it goes back to the 1950s, to John Wheeler, that you've got black holes and then you've got wormholes, and they sound the same, but they're not, because a black hole is a one-way journey to nowhere. You can fall in, but you can't get out. A wormhole has an exit as well as an entrance. So if you fall into a wormhole, you go through it, come out the other side. Where would you come out? Well, Jodie Foster did this in the movie Contact, and she came out near the star Vega. And you may remember her journey through, if you saw that movie, her journey through the wormhole was like being on the Northern Line and all this stuff that's flashing. And out she comes. But you could come out in another universe altogether, another space-time region, or another one of these bubble universes. But if you want to be really fanciful, as I like to be when I'm writing my books, that you could consider that if we got bored with this universe, or alarms that it was sort of running down to a heat death, we felt that there are better prospects elsewhere, could we decamp to another universe? Could we actually create a sort of black hole or a wormhole and go through it into, on the other side, what might be a fresh Big Bang? So Lee Smolin has suggested that could indeed happen, that the other side of the wormhole is a new universe, a bubble universe. So you decamp into that. That's emigration with a vengeance. It's getting out for good. It's leaving the whole universe behind to its dismal fate and starting off in a fresh new one.
Wormholes do not exist. We couldn't travel through them. And that claiming that they have created them in a lab is a total misrepresentation, and the people who did that should be ashamed of themselves.
Talking about wormholes, knowing that we're talking about nonsense, or terraforming Mars, knowing that we're talking about nonsense, that actually thinking, we're in real trouble, maybe we have to do fundamental physics at an incredible rate and render Einstein what Einstein did to Newton, an effective theory. When Einstein becomes an effective theory, we will realize that we do not live in space-time because, as is commonly said, the map is not the territory. If the map is Einstein's space-time, that does not mean that the underlying territory is space-time, nor does it mean that faster-than-light considerations have to dominate our future. It is the fact that it is not science fiction. I'm trying desperately to disagree with George so that this is interesting for those of you who got up. The issue is that it's not science fiction to get out of here. We don't know whether it's possible to get out of here, but we would have to go beyond Einstein. And the first thing you say in a seminar is let X 1,3 be a space-time manifold, which means you've invoked Einstein from the very beginning. It's very tough to get underneath Einstein. We should be spending our time and our effort on that. And I find it outrageous that we are instead talking about some stunt, which the community has been slow to denounce in the terms that it deserves. And I disagree with George. I think it should be denounced in even stronger terms.
It's good that wormholes became a science fiction fantasy, even though they are a science fiction fantasy, and maybe say something about how they became a science fiction fantasy in the first place, and about the origin of the whole concept. So when Einstein came up with general relativity and published in 1915, a few months later, this guy, Carl Schwarzschild, found the first true solution to the Einstein equations, which is the Schwarzschild metric, which among other things describes the black hole and the black hole interior. And it describes it all from a very particular perspective, and that perspective is someone very far away from the black hole, which is where you want to be. And from that perspective, Schwarzschild's equations describing the black hole had some very inconvenient elements that we call mathematical singularities, places where the math breaks apart. One of them turned out to be the event horizon, the place where time appears to freeze from the perspective of a distant observer. The other is the center of the black hole, the singularity, where everything gets crushed into a single point. Now, in order to understand the nature of the black hole, we needed a mathematical map of the black hole. And so some very clever people came up with a way to kind of change the coordinate system. We met a new coordinate system that allowed us to map our way across the event horizon. It turned out not to be a true mathematical singularity. It is something that you can fall into. And in this new coordinate system, various strange things appeared. So not just the event horizon, which once you're inside you can't leave. The singularity in the center of the black hole became not a point in space, but a point in the future, a point in time, an inevitable place that you would end up. But there was one way to escape the black hole, which is to, once you're inside, travel faster than the speed of light. If you travel faster than the speed of light and turn around, you can cross the event horizon the way you came in. But if you travel faster than the speed of light in the direction that you're falling, in this new abstract coordinate system, you don't hit the singularity, you pass through a sort of mirror event horizon, and you end up in a mirror universe. And this is the original notion of the what became called the Einstein-Rosen bridge. Okay, so in this new sort of abstract way of mapping the space in the black hole, we have a universe, we have the interior of the black hole, and then we have, if you keep following this same strange coordinate system, you end up in this mirror universe. And so this was the original notion. And so my statement is that the wormhole is essentially a mathematical fiction. It comes from pushing an abstract coordinate system too far and imagining that it is physical when it really shouldn't be imagined to be physical, or at least when we don't know how to interpret that.